We present OmniObject3D, a large vocabulary 3D object dataset for realistic perception, reconstruction, and generation. Our dataset consists of around 6,000 high-quality, real-scanned 3D objects from around 200 classes. For data collection, we utilize professional scanners to obtain a high-fidelity textured mesh of each object. Point clouds are sampled on the object surface, and multi-view images are rendered using Blender. We also capture videos using iPhones and extract foreground masks. With the vast exploration space offered by OmniObject3D, we set up 4 evaluation tracks: robust point cloud perception, novel view synthesis, surface reconstruction, and 3D object generation. We hope that the new dataset can boost research on general 3D object understanding and modeling in the real world. Existing advancements in the field of 3D objects partially meet the research requirements, but still fall short in various aspects. For instance, synthetic datasets like ShapeNet suffer from the disparity between unrealistic synthetic data and real-world observations. Video datasets like Code3D lack complete 3D ground truth information. Real-scan datasets like Google Scan Objects exhibit limitations in terms of category distribution. To address these shortcomings, we introduce OmniObject3D, a large vocabulary 3D object dataset that comprises an extensive collection of high-quality real-scan objects. Our dataset exhibits a long-tailed distribution, with an average of around 30 objects in each category, sharing common classes with popular 2D and 3D datasets like ImageNet, Coco, Elvis, and ShapeNet. Detailed comparisons with other relevant datasets are listed here. We now introduce 4 evaluation tracks on the dataset. First, we show how OmniObject3D boosts robustness analysis of point cloud classification by disentangling the following 2 critical challenges. Out-of-distribution styles are raised by the difference between CAD models and real-scanned objects. Out-of-distribution corruptions are introduced by common corruptions following the point cloud C dataset. We benchmark 10 state-of-the-art point cloud classification models in the table and review that robust point cloud perception models against both challenges are still underexplored. Please refer to the paper for more details. We next study several representative methods on our dataset for novel view synthesis under 2 settings. First, training on a single scene with densely captured images, which is the standard setting for NeRF. And second, learning priors across scenes from our dataset to explore the generalization ability for NeRF-style models. For single-scene optimization models trained on multi-view images from Blender, we observe that voxel-based methods like planoxels are especially good at modeling high-frequency appearance, while MLP-based methods are relatively more robust against ambiguities from difficult cases like concave geometry or textureless surface. When evaluating on both Blender renders and video frames on the same object, the error maps show how real captured videos introduce new challenges including motion blur, unbounded background, and reflections to the task. With a huge variety of shapes and appearances, our dataset provides a new evaluation benchmark for the task. Overall, the per-scene optimization models have already achieved considerable high-fidelity results, which encourages us to explore cross-scene generalizable frameworks. Accordingly, we evaluate several generalizable models on the dataset. We select 10 categories with the most various scenes, 3 objects from each as the test set. The models are either trained on each category except the test set, or trained on all categories except the 10 test categories. We can observe that OmniObject3D can serve as an information-rich dataset that is beneficial for obtaining a strong prior on unseen objects or even unseen categories. In particular, models that are trained on all categories tend to outperform those trained on a single category, which demonstrates the potential of a large vocabulary dataset to improve generalization ability. In addition to novel view synthesis, a precise surface reconstruction from multi-view images can enable a wide range of applications. With the accurate 3D mesh as ground truth, OmniObject3D can facilitate the evaluation of surface reconstruction models in both dense view and sparse view settings. Here, we show some results of surface reconstruction from dense view observations in our dataset, showcasing a remarkable diversity of geometry. We calculate the chamfer distance at the reconstruction metric. We split categories into 3 difficulty levels and observe a clear margin among results in different levels for all the methods. Compared with the standard DTU benchmark with 15 scenes, our dataset provides a more comprehensive evaluation on this task. Sparse view surface reconstruction is a particularly challenging task, and we observe significant artifacts in all of the reconstructed results. While sparseness demonstrated the best quantitative performance on average, it still falls short of real-world applications. MonoSDF heavily relies on the quality of geometry estimation results, making it less robust in some scenarios. We also evaluated the geometry of generalizable novel view synthesis methods such as PixelNerf and MVSNerf, which were found to be quite inaccurate. In summary, the problem of sparse view surface reconstruction has yet to be fully resolved, and our dataset provides a promising database for future research in this area. Besides reconstruction, OmniObject3D can also serve as a rich dataset to train a 3D generator of realistic 3D objects. We adopt the Get3D framework to generate textured meshes. We investigate its properties when learning many categories from the dataset using a single model. Here we show some examples of generated objects from different categories. We also show the cross-category interpolation results by interpolating both geometry and texture-latent codes from left to right. We analyze the bias in semantic distribution of the generated shapes due to the training data distribution. Please refer to the paper for more details. OmniObject3D is an ongoing project that involves a continuous expansion. We aim to collect a wide variety of 3D objects, ensuring a broader distribution and increased complexity across multiple modalities. Through these efforts, we hope that it can effectively support and drive advancements in many areas of the vision community in the future. Thank you for listening. Please visit our project page to access our dataset and code.